So today we will learn about testing. Testing is actually it's the process of finding errors. It's now pretty much universally accepted that the purpose of testing is to find problems. So you can never show that the absence of bugs or not through testing, right? So we can only prove the presence of bug. We cannot prove the absence of bugs. So here it raises a really important question, that is when to stop. When to stop testing is a very important question you have to ask yourself. And honestly, there is not very good answer to that because no amount of testing really will ever be sufficient to prove that your program works. So the purpose of testing is in a sense to prove that a program is no good. We can never test to prove that it's good. When we test and it produces errors, we simply say that program is not good. So software testing in and of itself is a process to find and hopefully lead to fix the defects in your implementation. So it's all related with bugs. And there is no way to prove that it's correct. Not really, not through testing anyway. But it's still a very important part of the process. You have got to make sure that you have quality inputs and you have the correct expected outputs. So actually all of these are going to come down to the critical question, should we release the software? And testing is the stage in the process where you say, no, we cannot release yet because the things are still wrong. So it becomes a very critical piece and also usually very time constraint in the process. So here I actually want to make sure that you understand the importance of testing in the software development lifecycle. So we have talked about system failures, errors. So what are those? So now when we say that a system fails, so a system failure occurs when the delivered service deviates from the specified service. So okay, that means that something didn't happen the way it was supposed to. So the failure occurred because the system was erroneous. There was error in the system. So an error is the part of the system state which is liable to lead to a failure. So a fault. So a fault is actually what happened. So what actually happened is the fault. So upon occurrence of fault, a mistake, it creates a latent error. That latent error sits in the code and becomes effective when it's activated. And that error actually causes a change in behavior that the user did not expect to see. That is a failure. So the error is a manifesto of a fault and a failure is the manifesto of an error on the servers. Let me give you an example. A programmer mistake, that's a fault, right? That's a mistake, that's a fault. The consequences of that fault is a latent error in the written software. So upon activation, when it uses that piece of data that's incorrect, that's when the error becomes effective. So when the effective error produces erroneous data or behavior, that is a failure. So we can have latent error that sit in waiting in a program for years before an input pattern finally actually runs that code in that way, and it produces a behavior that was not expected and therefore the failure. Now let's talk about the global view of the test process. So the box labeled P here denotes the object or the program that or the design document, etc., that to be tested, right? So that means the software under test. So P is defining the software under test. So the test strategy involves the selection of a subset of the input domain. Now here they actually give you the total picture, but it could happen that the whole software is not ready. So the entire software is not finished yet, but we want to actually test different modules. So you can test different modules. So you don't need the whole software to test. When your module is ready, you can test only this module, the smaller part, like a function, a subroutine, or a procedure, something small. So something small, some module is ready, and then you can test it with this test procedure. Okay, you don't need the whole system in your hand. So this is actually called unit test. You are testing a unit. So you will hear this word unit test a lot of time in the software engineering course. So unit test means that you will test a smaller part that's ready, that's already in your hand. So that's actually unit test. So to run a test against our software or against our unit, we must provide it with the information on which to act. So that means the input data, and it's also called the test data. So there are lots of ways that we can select or even generate the test data. We can generate the test data based on a profile we constructed of how we think the user will act based on probability or user studies, or we can attack the code with some data that often causes errors, or even inputting zeros, or we can put values that larger than what it asked for, or we can give it a word instead of a number, or this kind of thing. So however we get these inputs, these form our test data. So now for each of these inputs we run the software under test given the test data. So once the software is given the test data, we match the output, the behavior of the program given that input. So we will give the input, we will try to match the output. So the question then is what to do with that. Like, is it right? Has the software provided the correct result given the test data? Something has to do with that, right? Something has to say that it's true or it's correct. That something is called the oracle. So now traditionally, oracle has been the developer or the tester who is running the test. So the tester has the software running, they input the data, they watch what happened, and they decide whether or not the behavior match what they expected. So that's the total software test process. Now we have used test data in the software process. Now I will give you the idea of what test data and what test cases is. So you already know what is test data. Test data is just the input of the program, right? And now when we talk about test case are actually both the input data and the expected output. So you have the input data, you will decide the expected output. The combination of these two is called the test cases. Now I will introduce you to two different terms like verification and validation. You have seen these two terms in chapter 1 also. Verification and validation is really important terms in testing. So verification means that it confirms and performs to its specification. So we will write down what this will do. So this is actually the definition of if it does these things, it meets the user requirements. These kinds of relation. So now there is a big transition here between what the user wants and what we said we are going to do. So there is some room for error there. but we have to write down what we want to do that, right? What the software will do. We have to write down that, and so that we can give it to the developers, to the designers, to the architects, because they will actually build the system, right? So we write down those, and then we verify that what we build matches with what we set out to build. So this is actually, are we building the right thing according to what we wanted to build? So that's verification. So validation actually confirms to the user's satisfaction. So now what the user wanted and what they need are not necessarily the same thing. What they say they want and what they say they need, and what they actually want and need, can oftentimes be different things. So we have to actually validate on these two different levels. So validation is essentially, are we building the right thing? So verification is, are we building the thing right? And validation is that, are we building the right thing? So it's not just did we do what we wanted to do, but does the thing that we built is right? Is it actually good from a usability perspective? Is it good from a security perspective? Is it good just in a pure user satisfaction level? That's validation. So now we will discuss about various verification and validation activities which can be performed during the requirement engineering, design, implementation, and maintenance phase. The four essential criteria for a requirement specification are completeness, consistency, feasibility, and testability. So testing a requirement specification should be primarily aimed at testing these four criteria. So the aim of testing the completeness criteria is to determine whether all components are present and described completely. A requirement specification is consistent if its components do not contradict with each other, and the specification does not conflict with external specifications. And a requirement specification must be testable. In the end, we must be able to decide whether or not a system fulfills its requirement. So that's why requirement specification must be testable. So requirements must be specific, unambiguous, and quantitative. According to Poston, the most likely errors in a requirement specification can be grouped into three categories: missing information, wrong information, and extra information. So if we use a standard format for documenting the requirements specifications such as IEEE standard, it may help enormously in preventing these types of error to occur in the first place. And also, useful techniques for testing the degree to which the criteria have been met are mostly manual, like reading documents, inspections, reviews. And if requirements are already expressed in use cases means that it will have inputs and also the expected output. So in that way, the such scenarios are readily available. So in this way, a set of functional tests can be generated. And also at this stage, a general test strategy for subsequent phases must be formulated. It should encompass the choice of particular test techniques, evaluation criteria, a test plan, a test scheme, and test documentation and requirements. Next is the design phase. So during the design phase, we decompose the total system into subsystem and components, starting from the requirement specification. We may then develop test based on this decomposition process. So during the design phase, we may also test the design itself. This includes tracing elements from the requirement specification to the corresponding elements in the design description and vice versa. Well-known techniques for doing so are simulation, design walkthrough, or design inspections. So in the design phase, we can also formally document the resulting specification from the requirement engineering phase. The more formally the design is specified, the more possibilities we have for applying verification technique as well as formal checks for consistency and completeness. During the implementation phase, we do the real testing, right? That means the famous techniques are code inspection and code walkthrough. There are also many tools to support the testing of code. We have tools for static analysis and we have tools for dynamic analysis. We may try to prove the correctness of the code using formal verification techniques. All the techniques are aimed at evaluating the quality of the source code as well as its compliance with design specification and code documentation. The maintenance. We know that on average more than 50% of total lifecycle cost is spent on maintenance. So if we modify the software after a system has become operational, then we will have to test the system anew. This is called regression testing. To have this processed smoothly, the quality of the documentation and the possibilities for tool support are crucial factors. Now we will talk about two testing perspectives, black box testing and white box testing. In black box testing, it's actually you are not allowed to look at the code. In fact, you should know nothing about the code when determining how you will test the system to ensure it's working properly. So that means you have no idea about the code, but you will expect the output, right? So these are all behavioral approaches. That means if I do this, will it do this the way that I expect? So that's what black box testing. Now white box testing. White box testing, which is actually primarily based on the program structure. So black box was you have no idea about the code, but in white box testing it's actually based on the program structure. That means the code itself. These techniques are primarily about making sure that you test all the lines of codes and attack fragile or error-prone elements that had been used in building the program. Now we will talk about different stages of testing. So when we talk about unit testing, we are actually talking about testing of individual components. This usually means an individual method or potentially one class within the solution. Then module testing. The module testing is a set of units that come together as a collection or dependent components. So this is the first form of integration testing. So we have tested those smaller components individually. Now we will combine those together. We will make a module and we will do the integration test on this module. Now once the module are set up, we can do subsystem testing. So testing collections of modules integrated into subsystem. This testing is primarily concerned with ensuring that the interfaces between the subsystem and components, between the modules components, meet the specification that were given. Because suppose an individual developing team can build their module, right? Or even their component, and it looks like it works. But when we put them together, put all the components and modules together, they don't quite work the way they thought they would work together, right? So testing of this kind includes that integration of components, and it's making sure that components work together as intended. So that's subsystem testing. So going up again, we move from subsystem to full system testing. So testing the complete system prior to delivery. That's system testing. So there is a lot that goes into the developing team, making sure that the whole system is going work and also taking care of security concern, performance, usability, that the kind of thing. So we are actually testing the complete system prior to delivery. So that's system testing. So now we have acceptance testing. So it's actually a testing by users. Acceptance testing is actually testing by users. So that is sometimes called alpha testing, beta testing, and in fact it is true that in deployment once it's actually delivered to user, even though we don't call it an alpha or beta, when the user use it, they find bugs and report them back to us somehow. That's still a form of testing. It's probably the worst form of testing because you don't want those things, right? You don't want that your software is in real users hand and they are giving you the feedback that it's wrong. But it's still a form of testing and it's still a form of finding defects. So this is actually acceptance testing. So black box testing, white box testing, verification and validation testing, unit, model, component, system testing, acceptance testing, they are all just different ways of considering unit testing as a whole, broken into categories. But none of these are mutually exclusive. You should be well versed in all of the perspective techniques and employ each of them. Sometimes in isolation, for example, black box versus white box should be separated, but still you will use them together to get the best chance of successful overall testing.